will present our paper with title Genome Reconstruction Attacks on Genomic Data Sharing Beacons. And let's start with some background information. As you know, all human DNAs differ from each other, and the most common source of this variation comes from something called single nucleotide polymorphism, which is also called SNP shortly. These SNPs are also known as point mutations, where mutation occurs in single position in the DNA. In human DNA, there are two nucleotides in each position. One of them is called paternal allele, and the other one is called maternal allele. Here, for each position, a certain nucleotide is called major allele if it is the most frequently seen nucleotide for that position, and the other alleles are called minor alleles. For example, for that position, A is seen with 90% frequency, so A is the major allele for that position, and C is the minor allele for that position. And we categorize these DNA positions in terms of number of minor alleles that each position has. For example, 0 represents the homozygous major, where two major alleles occur in the same position. And 1 is for heterozygous minor, where a position contains one minor allele and one major allele. And 2 is for homozygous minor, where that position has two minor alleles. And why these SNPs are important? Because some of these SNPs are pathogenic and carry sensitive information about individuals. These SNPs, some of these SNPs cause genetic diseases, and also these SNPs carry information about health conditions and phenotypic traits about individuals. And our motivation comes from something called Beacon project that was introduced by Global Alliance for Genomics and Health in 2016. Here, the beacons are the genomic databases with certain data sharing mechanism. Here, in this system, users can send queries about particular SNPs to the particular beacons and receive a binary response for the queries. For example, a simple query is something like, is there a participant carrying nucleotide C at 1000th position of chromosome 1? And system either responds with yes or no. Here, no means that none of the participants in that beacon has that queried allele, and yes means that at least one of the participants in that beacon has that queried allele. And this system is designed especially for researchers to obtain an insight about genomic databases before receiving the genomes from these genomic databases. And several studies show that this beacon system is vulnerable to something called re-identification attacks. Here, in that attack scenario, attacker wants to learn whether a particular victim belongs to a particular beacon or not by sending some structured queries and using the responses for the queries. And today, I will present our newly proposed attack, which is called Genome Reconstruction attack. Basically, in that attack scenario, the attacker wants to partially reconstruct the genome of the victim. And by using that partially reconstructed genome, attacker initiates a re-identification attack. And let's move on to our threat model. In our threat model, attacker has the following information. Firstly, attacker has the information that the victim is added to a beacon between times t and t plus delta. And secondly, attacker has snapshots of the beacon at time t and t plus delta, basically before the victim is added and after the victim is added. Here, snapshot is the all possible query responses that are provided from the beacon. And thirdly, attacker has auxiliary information about the victim. This auxiliary information can be phenotypic traits or some part of the genome or the genomes of the father and mother of the victim, or it can be anything. And finally, attacker has access to publicly available information about genomics. And in genome reconstruction attack, attacker's goal is to reconstruct the partial genome of the victim. And also, by using that partially reconstructed genome, attacker's goal is to launching a re-identification attack into another beacon. And let's describe our attack scenario. In the first step, as I said, attacker takes a snapshot of the beacon before the victim is added to a beacon. And after that, victim with the newly added donor, other newly added donors join the beacon. And in the third step, attacker takes another snapshot. This time, victim and other donors added to beacon and saves responses. And in the fourth step, attacker reconstructs partial genomes from these query responses at time t and t plus delta. And how we can do that? Here, you can see that we have snapshots for each snip. We have snapshots at t and t plus delta. Some of these responses turn from no to yes. Some of them stay same as yes, yes, or no, no. But here, the valuable information comes from the SNPs that responded with no at time t and responded yes with time t plus delta. From these snapshots, attacker constructs this no yes response set from these snapshots. And next question of the attacker is how he can distribute these SNPs into different clusters to identify which of these SNPs belong to our victim or which of these SNPs belong to the other donors. Here, we use two initial approaches. First one is baseline approach, where we put these SNPs into different clusters according to MF information probabilistically. But this algorithm doesn't perform well because the distribution process is randomly done. In the next approach, we use greedy approach, where we start with empty clusters and put the SNPs into the clusters in the greedy manner according to the correlations between these SNPs. But again, this algorithm has the problem of cluster initialization and performs not that good. But our choice is clustering approach, where we build the graph, SNP graph from these noise response sets. Here in that graph, nodes are the SNPs and edges are the correlations between these SNPs. And we cluster these graph with two different techniques. First one is hard clustering, where our cluster does not overlap. For hard clustering, our choice is spectral clustering. The other technique is soft clustering, where these clusters can overlap. For that, our choice is fuzzy C-image clustering. After clustering these graphs, in the third step, we obtain partial genomes from these clusters. As it can be seen in the table. In the table, we have partially constructed genomes in the rows and SNPs in the columns. Here, 0 means that partially constructed genome has no minor allele in that position, and 1 means that partially constructed genome has at least one minor allele in that position. So our reconstructed genome represents the number of minor alleles by 0 and 1. And for evaluation, we use two different data sets. The first one is C population of the HapMap project, and second one is OpenSNP dataset. Here, we cross-validate our results with two different data sets, and also C population doesn't have any phenotypic information, and also OpenSNP dataset has the phenotypic traits. So we performed the additional experiments with OpenSNP dataset. And for metrics, we use precision and recall. And for that, we define the following metrics. For true positive, we define true positive correctly inferring a minor allele for SNP J, where victim has minor allele in that position. False positive is incorrectly assigning minor allele for that position J, where victim has no minor alleles in that position. And true negative is defined as correctly inferring no minor alleles in position J, and also victim has no minor allele in that position. And false negative is incorrectly assigning no minor allele for that position, but victim has at least one minor allele in that position. And let's move on to our results for the genomic construction part. For that, in the first experiment, we changed the number of related donors and used the fixed beacon size. Here in the x-axis, we have number of related donors, and in the y-axis, we have precision and recall values. As you can see, as the number of related donors increase, the number of noise responses increase naturally. And also precision and recall values stay high until a certain point. Our performance drops after a certain point because number of clusters that we need to cluster increase, and this brings the hard part for our clustering algorithm. We obtained 0.8 precision and 0.9 recall values with even with 5 related donors, and also we have reasonable numbers after 5. So we construct the new 5 million donors with really great precision and recall values. In another experiment, we change the size of the beacon by using fixed edge ratio. Here, we use 5%, which means that if we use a beacon with size 100, we add 5 new edit donors. Here again, precision and recall values stay high until certain point. For example, for beacon with size 200, we have around 0.75% precision and 0.85% recall values. But again, after some point, a number of clusters that need to do increase, so our performance drops after a certain point. But again, these beacon sizes are realistic ones. Even there are smaller beacons like 50 and 25, but we demonstrated the success of our attack with beacon with size 200. And this step is done. After that step, attacker now needs to identify which of these partial genomes belong to our victim. We have multiple partial genomes, and one of them belongs to our victim. So for that part, attacker needs to use something called auxiliary information. This auxiliary information can be anything. It can be part of the genome of the victim again, or it can be the genome of the father and mother of the victim, or a relative of the victim. But we assume the minimum possible information, and we use phenotypic traits that can be easily obtained from, for example, social media accounts or from the internet. We use non-sensitive phenotypes like eye color, hair color, or hair type, etc. For that, we trained random forest classifiers for each phenotype. After training these classifiers, we input these partial genomes into each classifier and calculate the probability score from each classifier. For example, from eye color, we calculate probability that this genome 1 implies the blue eye color, or genome 2 implies blue eye color, etc. We do this for all partial genomes, and we repeat this process for all phenotypes. After we calculating these scores, we sum the scores for each partial genome to calculate total score. And victim is matched with the partial genome that has the highest score. Here we use a technique something similar to ensemble of ensembles. And in the phenotype part, we obtain the following results. Here we have number of related donors in the x-axis and ensemble classifier accuracy in the y-axis. Here we obtained around 70% accuracy with 2 related donors and 42% accuracy with 3 related donors. But in that step might be much more simpler and successful, because if we use different auxiliary information, additional phenotypic information. But again, as I said, we assume the minimum possible information and use simple phenotypic traits to achieve reasonable accuracy values in that step. And even these accuracy values are enough for the next step, as I will show in a couple of slides. And after identifying the partial genome of the victim, attacker may want to initiate a re-identification attack against another beacon. This step is important because this re-identification attack can be initiated against a beacon that can carry sensitive information. For example, a beacon that contains people with the HIV disease. There are beacons similar to that. And if attacker understands that our victim belongs to that HIV beacon, for example, attacker can infer that this person has the HIV disease. And attacker, this is I think the cool part of our attack. Attacker learns that sensitive information by only using the information that this victim that will be at some time point, and also using some simple non-sensitive phenotypic information. And from these two information, attacker concludes that a victim has that disease, for example. And for re-identification attack, we use optimal attack where the minor allele frequencies of the population is used. And in that attack, attacker queries SNP according to the ascending MAF order. And even 5 or 10 queries are enough to determine the membership. And you can see the result of the membership inference part. In the x-axis, we have number of queries, and in the y-axis, we have power. Here, power implies the confidence level of the attacker. Power 1 means that attacker can 100% confident say that this victim is belong to that beacon or not. Here, we have 0.8 power with 2 related donors and 0.7 power value with 3 related donors, which are, I think, successful results for that part. And for conclusion, we currently know that beacons are vulnerable to re-identification attacks, and these dynamically changing beacons can cause some serious privacy issues. And with our newly proposed genome reconstruction attack, we showed that a part of the victim's genome can be reconstructed successfully, and that reconstructed genome can be used in re-identification attacks successfully, as I showed previously. And we have shown the practicality of the identified privacy concern with our experiments, and also we somehow show the countermeasures to avoid such kind of attacks, because when, for example, number of related donors increase, our performance drops, or when the beacon size increase, our performance drops. So increasing beacon size on related donors with, can avoid such kind of attacks. And thanks for listening. You can ask any questions and contact me from this email address. Thank you.